So the wheatstone bridge circuit is a circuit, it's not an instrument. You wouldn't get any instrument in the lab of this nature. So its function is to compare the resistance of resistors, and two, it is also used to determine the resistance of unknown resistors. So one used to compare resistances, and two, used to determine the resistance of unknown resistors. Unknown resistors. These are the two key functions of the wheatstone bridge circuit. Okay. Now, the wheatstone bridge circuit work or operates, it works the circuit operates on the principle of now, on the principle of now slash or zero deflection. So this is the principle on which it works. It works on the principle of now or zero deflection of the galvanometer. Okay. When the galvanometer reading, when the galvanometer reading is zero, the bridge is said to balance, is said to be balanced. Okay. So the whole wheatstone bridge circuit, there are four, the wheatstone bridge circuit, wheatstone bridge circuit has four resistors. One unknown, and the remaining three, are known resistors. The remaining three are known resistors. However, one of them must be a variable, resistor. So these are the four resistors: R1, R2, R3, and R4. R4 is a variable resistor. It's a variable resistor. Are you there? Hello, are you there?
Yes, please.
Okay, so the variable resistor is what is shown or indicated as this. Okay, so R4 is a variable resistor, meaning one of it is such that its resistance is unknown. Let's represent, it can be any, but let's represent R3 by Rx. X to mean that it is unknown. X to mean or to indicate that it is unknown. Now, meaning R1 is, Josephine, are you there?
Yes, please. I was calling Aduma.
What's the feedback?
She didn't pick.
She's still sleeping. Okay, let's continue. Bella, Bella. Bella.
Yes.
All right. So now let's look at its operation. Or let's wait for Equia to call Bella. Equia, when you finish, let me know, okay, so I can continue. Josephine, were you able to solve the Kirchhoff's law questions?
Dear, please, you can continue.
Josephine. Josephine. Hey, she's still not active. Okay. Let's have Josephine's attention. Call her as well. Josephine, are you there? Okay, she's gone. All right, Equia. So, Watson, are you there?
Yes, please.
Okay. So when the circuit when the key is closed, of course, the source of EMF will drive current through the circuit. Now, when the current I gets to the junction A, okay, it will break up into I1 and I2. By whose law? It will break up into I1 and I2 by whose law?
Catch off.
Kirchhoff's which law?
Current law.
The current law. So we have I1, I2. Now, as I said, R4 is variable, meaning its value can be changed with time. So it's a try and error kind of thing. Okay, as we vary this resistance R4, don't forget R1, R2 are known. Rx is unknown. But R4, which is also known, is a variable one, meaning we can vary this resistance at any time. Okay. The function of the galvanometer here is to measure the current flow as R4 is being varied. As R4 is being varied, there will be a particular resistance of R4. There will be a particular resistance as R4 is varied where the galvanometer reading, where the galvo will read 0. Galvanometer reading will be 0. Okay. Because R4 is variable, as we vary R4, there will be a particular value of R4 where the galvanometer will read 0. Okay. Now, when the galvanometer reads 0, when galvanometer reading, when G is 0, what it means is that no current flows through the galvanometer, through the galvo. But what causes the 0 reading of the galvanometer? Yes. What accounts for the 0 reading of the galvanometer? Yes. And we are just saying that what is responsible for the 0 reading of the galvanometer? Fatima and Josephine, are you there?
Yes, please. We said,
What
I think most
mhm.
of the current flow.
What is the cause of the 0 reading of the galvanometer? Josephine. Josephine, are you there?
Yes, please. Just I'm thinking about it.
Okay, listen. R, I said R1, R2 are known resistors. Rx is unknown. R4 is variable, meaning we can vary it at any time t. So as we vary R4, maybe 1 ohm, 2 ohm, 3 ohm, and we are varying it so that the galvanometer will read 0. So as we vary R4, there will be a particular resistance of R4 where the galvanometer will read 0. So what is responsible for the 0 reading of the galvanometer? What?
We said, I think because of the current flow.
It is actually because of the variable resistor. Okay, R4 is variable. So as we vary it, there will be a particular resistance where the galvanometer will read 0. So galvanometer is reading 0 due to the variable resistor. Is that okay?
Yes,
Yes.
please.
I'm just probing to make sure you are following what is being said. Okay. Now when galvanometer reads 0, what it means is that the PD across the point B, the potential difference across the point B and the potential difference across D are the same. Okay, when galvo reads zero, it means V at B is equal to V at D. Of course, when 2 points have the same potential, no current would flow. Current would only flow on condition that the 2 points have different, they have a potential difference. But when 2 points have the same potential, current flow is zero. So if the galvanometer is not reading and its reading is zero, then it means that the PD across the point connecting the galvanometer is the same. Please, are you okay with this?
Yes, please.
Okay. So current, the source current is high. Kenneth, are you following?
Yes, sir.
The source current is high. When it gets to the junction A, it will break up into I1 and I2. Now, when it gets to this junction B and D, ideally, they are also to break up. But because of the zero reading and the fact that the PD of B and D are the same, current will not flow through the galvanometer line. It will continue through Rx. I2 will continue through Rx, and I1 will also continue through R2. And it will not pass through the point BD because they have the same potential. If you have watched my Josephine and they are you okay?
Yes, please.
Okay. Now, when you consider the loop, considering loop A, B, D, E, and applying Kirchhoff's voltage law and applying KVL, Kirchhoff's voltage law. I have somebody to help me. We are moving through the loop A, B, D, A. So help me apply Kirchhoff's voltage law to this taking loop. Okay, what now?
It's the idea.
Help me apply Kirchhoff's voltage law to the loop A, B, D, A. Application of knowledge. We've done this. So
Okay, Mr. Diasu, E will be equal to
is there any E within the loop? Is there any source of EMF within the loop?
no.
No. So zero, the EMF is zero. So zero is equal to
I2R4 plus.
we are moving A, B, D, A.
Okay, I1R1
I1 times R1.
plus
Open your eyes.
0.
AB, considering the loop A, B, D, A. What will be the PD across R4? Minus I2 R4, isn't it?
Yes.
Do you understand why?
No, please.
Because the direction of the current I2 is going against the direction of the loop. This is the direction of the loop. We are taking the loop A, B, D, A. So when you go to the resistance R4, the direction of the loop is going against the direction of the current I2. And therefore, the PD must be negative. Are you okay?
Yes, please.
Josephine, are you okay? Watson, are you okay? And Calvin,
Yes.
Kennedy,
Yes.
go. So that's why, and I'm equating this to zero because there's no EMF here. Therefore, I1 R1 is equal to I2 R4. Take this to be equation 1. Let's consider another loop. So considering loop BCDB, BCDB, Equia, Boatman, take me through the Kirchhoff's voltage law. Considering the loop BCDB.
Okay. It says 0 is equal to
0 is equal to just
it's
take.
the
Okay, go ahead. We are going by the loop BCDB.
I
I what? I told you that when the gavel reads 0, I1 will not pass through the gavel, but I1 when it gets to B will still pass through R2, and R2 when it gets to D will not take BD, but they will still go through RX. So look at it and tell me. 0 is equal to,
I2 R2.
come again.
I2 R2.
Which current will go through R2? Will it be I2 or I1?
I1.
I1. So I1, we are following this loop. So I1, Josephine and Kenneth, are you also following, please?
Yes, sir.
So
Yes, sir.
I1 R2, here. Josephine, continue. I1 R2
Minus
minus
I2 RX.
I2 RX. Thank you. Are you okay?
Yes, please.
Okay. Therefore, we can say that, yes, I1 R2 is also equal to I2 RX. This is equation 2. The next thing that must be done is that we divide equation 2 by equation 1. So just take over. Divide equation 1 by 2.
Mm.
1 by 2.
So, I give the final answer?
Take me through.
Okay. I1, R1
I1, R1,
on I1, R2
I1, R2
is equal to I2, R4,
is equal to I2, R4
R4 all
over,
on I2, RX.
and so I1s will cancel out, I2s will also cancel out, and we have R1 over R2 is equal to R4 over Rx. This is the condition at the balance point. Condition when the bridge is balanced. Okay, this is the condition when the bridge is balanced. Now look at something. When you look at the bridge, look at the upper arm of the bridge. The upper arm of the bridge is R1 and R2. It is similar to your arm. Okay. Above, when you raise your left arm, okay, what is there is R1, R2. And then your other right arm, when you turn it, is also R4 and RX. So when the bridge balances, this ratio, the ratio of the resistances are the left arm. So R1 will be divided by R2. And your right arm, when it balances, will be equal to, also be equal to R4 divided by Rx. So when it balances, the upper resistance, the ratio of the upper resistances must be equal to the ratio of the lower resistances. So that is the condition at the balance point. This is the whole nitty-gritties of the Wheatstone bridge circuit. Are we okay? Are we okay?
Yes, sir.
Is there any question? So at the balance point, we have R1 over R2 equal to R4 over Rx. Now with this, because R1, R2, and R4 is known, you can determine the unknown by simply making the unknown the subject, which would be R2 times R4 over R1. So knowing R2, R1, and R4, you can easily find the unknown resistance. There we are you okay?
Yes, please.
Janet, are you okay? It's just not difficult, but you just must understand it. Let's look at the meter bridge. The meter bridge. As I said earlier, there is no instrument in the lab known as the wheatstone bridge. But in the lab, you find the meter bridge. So the laboratory application of the wheatstone bridge circuit is the meter bridge. The laboratory application of the wheatstone bridge principle is the meter bridge. So in the lab, you find a meter bridge, which basically applies the principle of the wheatstone bridge. Now, the meter bridge circuit. You see, in the wheatstone bridge, there are 4 resistors connected in that bridge form. The meter bridge, you find 2 resistors. The remaining 4 is compensated by the length of a wire, a constant wire. So the meter bridge circuit, you find something like this. R1, let's say R1, or let's represent this by R and P. Resistance R and P instead of 1 and 2, it can be okay. Let's follow what we've done before so that you can connect. So R1, R2. Then this is connected to a length of wire, a wire of length 100 centimeter or 1 meter. That wooden board. So the wheatstone bridge circuit. I'm sure you've seen the meter bridge in the lab before.
Yes, please.
Because current must flow through it, there is a battery. Then there is a key. Because we want to always control the flow of current. This is key. A, B of length 100 centimeter or 1 meter. A galvanometer is connected at a point. Then connected to the galvanometer is a jockey. This is the wheatstone bridge circuit. Now the meter bridge circuit. So R1, R2 are here. The variable resistor. Don't forget resistance of a conductor is rho L over A. So when you choose a certain length of the wire, it is directly proportional to a certain resistance level. Don't forget R is directly proportional to L, since rho and A are constant. So varying the length of the wire AB varies the resistance. Are we okay? So the length of the wire AB is there to compensate for the variable resistance. As we vary the length, we are varying the resistance of the wire or of the conductor. What are you okay?
Yes, please.
You connect and Josephine.
Yes.
Okay.
Yes.
So when you choose 10 centimeter, it has its own resistance it will introduce. And because the whole length is 100 centimeter, if you choose L, the remaining length will be 100 minus L. Okay, so L will introduce a certain resistance, will compensate for maybe R4, and the remaining 100 minus L would also compensate for Rx. Okay, so in all, by varying the length of the wire, we more or less have the four resistors. Yes, the four resistances. The current I flowing through the circuit is this. When I gets to the junction A, it will break up into I1 and then I2. Now, as we vary the length of the wire or the conductor, a particular length will set the galvanometer into null or zero deflection. So as we vary the length of the constantan wire, a particular length L will set the galvanometer into a null or zero deflection. Okay, so at that length, the galvanometer would reach zero, meaning that assuming we have A, B, C, D, E, no current will flow through the point JD because they are at the same potential, meaning V at D is equal to V at J. So I1 will flow through R1 and will continue to flow through R2. I2 would flow through L and will also continue to flow through 100, the length 100 minus L. Please, are we okay?
Yes, please.
Okay, what are you fine? And then connect.
Yes, please.
Okay, just the same wheatstone bridge method. So when you take the loop, if you take the loop, you have I1 times R1 loop, clockwise loop. If you take a clockwise loop, you have I1 times R1 minus I2 times L equal to 0. The same thing we got. Then when you take the other loop, another clockwise loop, you have I1 times R2 minus I2 times 100 minus L also equal to 0. Therefore, I1 R1 is equal to I2 L, equation 1. Then I1 R2 is also equal to I2 times 100 minus L. And this is equation 2. So when we take ratio of equation 1 and equation 2, we'll have R1 over R2 is equal to L over 100 minus L. Therefore, if one is unknown, you can easily, assuming R1 is unknown or R2 is unknown, you can easily determine R1 or R2. Or R2 is equal to 100 minus L all over L times R1. These are the meter bridge equations. These two are the meter bridge equations, which are even used for meter bridge experiment graphs. Plot a graph of Rx over 1 over L or 100 over this kind of thing. So this is the meter bridge equation. So the laboratory application of the wheatstone bridge circuit is the meter bridge. Please, are we okay?
Yes, bro.
If you have any question, quickly ask. If we are bottom, or if you are no question,
No question.
then it.
No, please, no.
So you see, it's not so difficult. You just must understand it and then know what to do. That's all. Okay. Let's see how this is used in solving questions or problems. In a meter bridge circuit, I'm reading the question. In a meter bridge circuit, the null point is found at a distance of the null point in a meter bridge circuit. The null point is found at a distance of 40 centimeters from A. In a meter bridge circuit, a null point is found at a distance of 40 centimeters from A. If a resistance of 12 ohm is connected in parallel with S, if a resistance of 12 ohm is connected in parallel with S, the null point occurs at 50 centimeters from A. If a resistance of 12 ohm is connected in parallel with S, the null point occurs at 50 centimeters from A. Determine the value of R and S. Determine the value of R and S. This is what they are saying. R1 is represented as R. R2 is represented as S. Now, in a meter bridge, the null point is found at a distance of 40 centimeters. So where we have just R and S, the meter bridge balances at a distance of 40 centimeters from A. So when you measure 40 centimeters from A, then the jockey must be placed at where 40 is. And that is the point where the bridge balances. So when this is 40, the remaining length is 60 centimeters. Then, if a resistance of 12 ohm is connected in parallel with S, so if we connect a resistance of 12 ohm in parallel to S, this is another resistor. The resistance is 12 ohm. When it is connected in a parallel manner or way to S, we are told that the balance point this time is 50 centimeters. Determine the value of R and S. Please, can you try? Can we give it a try? What man good? Talk to me.
Yes, please.
Okay, so try it. Let's see.
Mr. Dia,
Hello.
this my next step was maybe we are supposed to find I raised what is
Um,
the latter
deter
part of the question.
let me know where you got to.
Um if a resistor of 12 ohm is connected in parallel with S, the null point occurs at 50 centimeters from A.
Determine the value of R and S. Leonard, are you there?
Yes, sir.
So this is the circuit. When we have just R and S, the null point is obtained at 40 centimeter from A, meaning the remaining length will be 60. Then in a second situation, when a resistance of 12 ohm is connected parallel to S, the null point this time is 50. So 50 centimeter, 50 centimeter. Determine the resistances RS and R and S. Are we through? we are watching Kenneth and Joseph. Are you true?
No, sir.
Aria. Aria. Okay. I think because of time, let's look at it. Because of time, let's look at it together. And then I'll give you other examples to try your hindsight. Hey, the late Bella. You were sleeping.
Yes, please.
Hmm. Okay, so in the first case, we know that for meter bridge, R over S must be equal to L over, sometimes L1 over L2, but if L1 is L, then L2 would be 100 minus L. So it means that the initial resistance is R over S, then the balance point will be 40 over 60, which is also equal to 2 on 3. So we have R over S to be equal to 2 over 3 at the first balance point. Then at the second balance point, this time S changes a little bit. S is now connected to a 12 ohm resistor. So the total or the equivalent resistance, S equivalent in this case, must be 12 times S over 12 plus S in this case. Please, are we okay here? Hello, are we okay?
Yes, please.
So 12S over 12 plus S, because S and the 12 ohm resistor are connected in parallel. Meaning that if we take a ratio of this, we'll have R divided by, let me write for it. R divided by S equivalent must be equal to 50. L is 50. Then 100 minus L is also 50. R over 12S all on 12 plus S must be equal to 1 over 1. Okay, so you simplify this. R over 1 all divided by 12S over 12 plus S. Okay, so 1 on R on 1 times 12 plus S on 12S must be equal to 1. This is equation 2. So solve equation 1, which is 3R is equal to 2S, or how you take it. If R is equal to 2 over 3S, then you substitute that into equation 2 to determine S. When you finish, you then find S. Please, are you okay? Are we okay?
Yes, please.
So please finish it for me and then give me the final answer.
Please, S is 2.4 ohms.
S is
2.4 ohms.
check again. That's not what is stated here. From this equation, please, we can also say that R is equal to 12S over 12 plus S. Okay, without necessarily doing this, we can just make R the subject from here, cross multiply, and we'll also have R to be equal to 12S over 12 plus S. So Josephine, check it again. Let's see.
The area please is S6.
Yes, S is 6.
Yeah. So beside S to be 6 and R to be 4.
Exactly. S is 6, R is 4. Josephine, cross check and let's see.
Please, I had the same answer.
Okay. So that's it. Okay. Not a difficult question at all. All right. The wire AB, another question. The wire AB shown in the diagram below is 400 centimeter. I'll give you the diagram. So the wire AB shown in the diagram below is 400 centimeter long. Where should the free end of the galvanometer, it refers to the jockey, where should the free end of the galvanometer be connected on AB? Where should the free end of the galvanometer be connected to AB so that the galvanometer shows no deflection. Let me give you the diagram. Where should the free end of the galvanometer be connected on AB so that the galvanometer shows no deflection? There's the diagram. So let me. Take the diagram like that. So and you are told that the wire AB shown in the diagram below is 400 centimeter long. So where should the jockey be placed on the wire so that the galvanometer would show no deflection or zero deflection? If AB is 400 and the resistances are 8 ohm and 12, start with. Are we done?
Yes, please.
What's your answer?
The free end of the galvanometer should be placed 160 centimeters from A.
Exactly. That's the answer. Okay, what did you get? 160.
No, please.
You couldn't get that. Kenneth, you too.
Yeah, please, I had a 160.
Okay, Josephine. Take us through so that Equia would identify where she went wrong.
Yes, please. So since I didn't know the distance, I presented A to where the jockey is to be L. The length from A to where the jockey is to be L. Then from the jockey to B to be 400 minus L, because they say the total length AB is 400 centimeters. Then I took the ratio. So 8 on 12 is equal to L on 400 minus L. Yes. And I made L the subject. And I got it to be 160 centimeters.
Fatima,
Mr. Elia.
are you better?
Yes, please.
Okay. So meter bridge, and no. The potentiometer circuit. The potential. So we use the wheatstone bridge circuit, whose practical application is the meter bridge. We use it to compare resistances of resistors and also to determine the resistance of an unknown resistor. The potentiometer, on the other hand, the potentiometer circuit, on the other hand, is used to also compare EMF of sources and also to determine the EMF of an unknown source. Okay, so its usage is also to the potentiometer circuit is also used to compare the EMF of sources and also used to determine the EMF of an unknown source. And three, it is also used to determine the internal resistance the internal resistance of sources of EMF. So these are the three main functions of the potentiometer circuit. One, to compare the EMF of sources. Two, used to determine the EMF of an unknown source. And three, used to determine the internal resistance of sources of EMF or of batteries or cells. Okay. Now, it also works on the principle of null deflection. The potentiometer circuit also works on the principle of null deflection. Okay. Now, it works on the principle that when there is a constant current flowing through a conductor. So let me draw another circuit. This is the length of the wire. We often use 100 centimeter length of the wire. A source of EMF. This is a resistor. This is a Q. So A, B are the ends of the constant wire. Then when we connect a voltmeter to a jockey, this is not the galvanometer yet. This is the voltmeter. So long as the current flow through the wire or the circuit is constant, when there is a constant current, flowing through a circuit, the voltage drop across any section. Let me write in words before. The PD across any section of the wire is directly proportional to the length of the wire. So change in voltage across the length of the wire is directly proportional to the length of the wire. So you see, V is equal to I times R. Since this is a conductor, resistance of a conductor is equal to the resistivity times the length times divided by the cross-sectional area. Now, rho, for the same wire, rho and A are constants. Okay, rho and A are constants. So if you put V is equal to I, R is rho L over A. If you are able to maintain constant current flow through the wire and the resistivity for the same wire, its resistivity will not change. For the same wire, its cross-sectional area will not change. Then K is equal to I rho over A. Okay. K, the constant. So we have the constant is equal to I times rho over A. So V is virtually equal to KL. Because K is constant, then we can say that V is directly proportional to the length of the wire. Please, are we okay? Are we okay?
Yes, please.
So within the circuit, if you are able to maintain the constant current flow through the circuit, because the resistivity, the length, the cross-sectional area of the wire is constant, then you can say that the voltage drop across any section of the length is directly proportional to the length of the wire. So delta V is directly proportional to L. Just is the basic principle or the concept behind potentiometer. So in the lab, if you are given, you see, E, R are there to give you a constant current flow. And so when you connect a voltmeter across any length of the length of the constant wire AB, the voltage drop, which is the voltmeter reading, must be directly proportional to the length of the wire, meaning that as the length of the wire increases, the voltage drop also increases. So this is what we investigate during practical. You will be given varying lengths of the wire and be asked to measure the voltage. Maybe starting from 100 in that decreasing order. 100, 90, 80, 70. But all that you need to understand is that for potentiometer, the voltage drop is directly proportional to the length. So as the length increases, voltage drop must also increase. As the length decreases, voltage drop must also decrease. Yeah, are you okay?
Yes, please.
Kenneth, are you okay?
Yes, sir.
So when you understand this, in fact, your laboratory practicals on meter bridge and potentiometer, simple. It is not difficult because this is just the foundation. Now the constant, you see, we had V is equal to K times L. K, which is equal to rho L, rho, let me, K, which is equal to I times rho over A. This is known as the potential gradient. Potential gradient. So note something. If you are given L, whether increasing or decreasing, and you are asked to measure the voltage drop across the length of the wire. Once it's in that decreasing order, the trend of the V is that it must also be decreasing. Now, if the graph has that plot, or if the sub-question has that plot a graph of maybe V over L. Plot a graph of, after getting your values, plot a graph of V against L and find the slope. Of course, once the trend is that as L changes, increases or decreases, V also decreases. You must have a straight line. When you find the slope of this graph, which is change in V over change in L, what do you think the slope of this graph will represent? What do you think will be the significance of this slope? Anybody? Josephine, Ekuya, and Kenneth, what do you think will be the significance of this slope? Josephine?
You say there is a potential gradient.
Exactly. From the equation, I told you that V is directly proportional to L, and V is equal to a constant L. So your K is V on L. So if you are to plot voltage drop against length, then it means that the slope is equal to the potential gradient, which theoretically you know to be equal to I rho over A. So they can use this even as a sub question, knowing that the slope of this graph is equal to the potential gradient. They can ask that find S is equal to IP over A when you are given certain parameters and be asked to find maybe rho I or A. Okay, depending on what information will be given here. Please, you understand it? Well, S is the slope which can be determined from the graph. So when certain information about the conductor, maybe its resistivity and the cross-sectional area is given, you can be asked to find I. Just this simple. Ekuya, do you understand? What man? Or she
Yes,
Kenneth, do you understand?
Yes, sir.
So I always say that practicals is theory. When you understand the theory, it is very, very simple. It is very, very simple. Okay. Let's look at, so this is the principle behind the potentiometer. Okay. As you vary the length, now the precautions is that the precautions are and potentiometer is that when you are measuring the length as given, maybe in increasing order or decreasing. the jockey, which is this, must not be slashed over. Okay, you shouldn't put the jockey on the wire, press it, and then scratch it along. When you do that, with time, you will change the uniform cross-sectional area of the wire. With time, you'll be changing the uniform cross-sectional area of the wire. 2, which is key, is that friction raises the internal energy of bodies. That is why when you scratch your 2 palm, when you rub it together, it generates heat. So as the jockey is scratched on the wire, it introduces heat. When heat is introduced, it will change the temperature, goes with resistivity. So when heat is introduced, it will also increase the resistance. And when resistance is changed, it will subsequently or consequently change the current flow through the circuit. Don't forget that under this experiment, the concept is that when constant current flows through the circuit, the voltage drop across the length of the conductor is directly proportional to the length. So as you are scratching and it is generating heat, heat would change the resistance. When the resistance changes, it would affect the constant current which must be obtained so that the experiment will be obtained or would take place successfully. So as a precautionary measure, we do not slide the jockey over the wire. We do not slide the jockey over the wire because apart from changing the physical property of the wire, it will also increase the resistance and will affect the constant current which must flow. Ekwe, are you okay?
Yes, please.
Josephine, are you okay?
Yes, please.
Kenneth.
Say, right.
So in potentiometer circuits, this is a key precaution. Note that. All right. The other applications using it to compare the EMF of sources or cells. That is the circuits that have been drawn here. It's unfortunate Apia Adoma and Co could not join because this is the meter bridge, the potentiometer part, very, very important concepts.
Please, they said they're waiting for the video since they couldn't join.
I cannot wait for them. And the video cannot wait for them. Okay, so we'll have a class this evening too. Okay, I'm supposed to attend a funeral, but because of you, I had to. The plan is to be there tomorrow. So do we leave the 2 uses for evening's class?
Yes, please.
Since we are almost doing 2 hours, let's and just let's leave the 2 for evening class. Are you okay?
Yes, please.
All right. Okay. Then hopefully we'll continue it in the evening. Okay. From as usual from 7 to 9. Okay. Bye bye. Kenneth and go. Bye bye.
Uh, All right.
Bye.
Mr. Jen,
Hello.
please can you send me Thursday's evening video?
Come again.
Thursday's evening video.
Uh,
Thursday evening the
we
video.
uh we we basically solve questions on um uh uh Ketchup's law. That is why I sent
Um,
those questions to you.
okay, I'm on it. I'm going to read. Look at the last one.
Come again.
And then I'm on it. I've solved three of the questions. Look at the last one.
So do it and forward it to me. Okay.
Yes, please.
So that is why I did not send it to you, because we basically solved questions.
Yes, please. Thank you.
Oh, okay. Okay.